Hello and welcome to my lecture series for Control System 1, which is designed for 5th semester B.Tech in Electrical Engineering students. Myself, Shumon Ghosh, as a course coordinator, assistant professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This particular PPT is designed for lecture 13, 14 and 15. And today is our 13th session. So, moving to our module. In this module, there is time domain analysis. In time domain analysis, the sub-modules are time domain analysis of a standard second order closed loop system, determination of time domain specifications of the system, step and impulse response of first and second order system. These three sub-modules I already discussed in lecture number 12 and 11. And in our today's lecture, we will discuss stability by pole allocation, Routh-Hurwitz criteria, and application. And in our last two lectures, we will discuss control action, and there is PI, PD and PID controller. So this particular PPT is designed for lecture number 13, 14 and 15. And in our today's 13th lecture or 13th session, we will discuss on characteristics equation, pole locus of a second order system with variable damping ratio, that is zeta, and stability by pole allocation. These 3 points I will discuss in this particular lecture. And the rest of the contents, that is Routh-Hurwitz criteria and its application, some workout problems related to Routh-Hurwitz criteria and relative stability, these 3 points I will discuss in lecture number 14 and 15. So moving to our first point or first topic, today's first topic, that is characteristics equation. Now what is characteristics equation? To understand characteristics equation, let us take one standard closed loop control system. This is a closed loop control system, block diagram of a closed loop control system, where RS is the reference input, CS is the controlled output, GS is the forward path transfer function, HS is the feedback path transfer function, and ES is the error signal. So, if we calculate closed loop transfer function for this system, then we can get CS by RS is equal to GS by 1 plus GS into HS. The process of finding this type of closed loop transfer function we already discussed in our previous lectures. So just follow the previous lectures. So this is our closed loop transfer function, that is GS by 1 plus GS HS. Now the denominator part of this closed loop transfer function, that is 1 plus GS into HS, is called as the characteristics polynomial. Now what is characteristics equation? This is characteristics polynomial, and the characteristics equation is like this: 1 plus GS HS is equal to 0. This is our characteristics equation. Now why it is called characteristics equation? To understand why it is called characteristics equation, let us take one example, that is a standard second order underdamped system transfer function. This is basically the transfer function of a standard second order system, where Cs by Rs is equal to omega n square divided by s square plus 2 zeta omega n into s plus omega n square, where omega n is the natural frequency, zeta is the damping ratio. So for this particular transfer function, if we want to calculate the characteristics equation, or if we want to identify or find the poles or the roots of the system, then we have to put the denominator part is equal to 0. That is s square plus 2 zeta omega n into s plus omega n square is equal to 0. And if we calculate the values of s from this particular equation, then those values of s will be our roots or the poles of the closed loop system. So if we apply Sridhar Acharya's rule here for this equation, then we can get two roots, that is s1 and s2 is equal to minus zeta omega n plus minus j omega n root under of 1 minus zeta square. So these two are the roots of the standard second order control system. Now a study of roots, that is S1 and S2, gives a prediction about the nature of the system or the nature of the time response. The real part of the roots represents the damping, that is minus zeta omega n, that is our real part. That real part represents the damping, and the imaginary part, that is plus minus j omega n root under of 1 minus zeta square, that is our imaginary part, which represents the damped frequency of oscillation. Now, depending on these particular roots which comes from this equation, we can say or we can predict the nature of the system. That's why it is called characteristics equation. Whether the system is stable or unstable, we can say from this equation by calculating the roots. That's why s square plus 2 zeta omega n into s plus omega n square is equal to 0. This equation is called characteristics equation of a standard second order system. And in general 1 plus GSHS is equal to 0. That is our equation of characteristics equation in general. And for second order system, standard second order system, s square plus 2 zeta omega n into s plus omega n square is our characteristics equation. Now just look at the figure. The topic is time response of a standard second order system depending on the damping ratio, that is zeta. In our lecture 12, we already see the process how we can calculate the time responses of the second order control system depending on the damping ratio zeta. Here we can conclude like this. Now if zeta is equal to 0, that is our first condition. If zeta is equal to 0, that is undamped condition. If you put zeta is equal to 0 in this equation, in this equation S1 and S2, if you put zeta is equal to 0, then you can find that we can get two values of S1 and S2. That means the poles of the two systems will be in the imaginary axis, and this is our imaginary axis, this is our real axis. If you put zeta is equal to 0 in this particular equation, then we can get S1 and S2 is equal to plus minus j omega n only, as this term, real term, will be 0 and these root over terms will be 0. Okay, root over term will be 1, so that's why only plus minus j omega n will be there if you put zeta is equal to 0. That's why the two roots are present in the imaginary axis. Now for the undamped system, in our lecture 12 we see that for undamped system, for zeta is equal to 0, the time response will be like this, and this will be in oscillatory in nature. So this is our time response for undamped system. That's why we can say if the poles of a system are present in the or the complex conjugate poles, better it is complex conjugate pole. Complex conjugate poles are present in the imaginary axis, then the response will be oscillatory in nature. Like this way, if we want to calculate or if we want to take underdamped case, that means zeta will be in between 0 and 1, then we can find S1, S2 like this, that is negative real axis, that is complex conjugate pole with negative real axis. Okay, like this is our complex conjugate pole with negative real axis. And for underdamped system, the response will be like this, it will be settled down after a certain time. So this is our underdamped case or underdamped time response. So we can say if the poles are in the if the complex conjugate poles are present in the negative real axis, then the response will be like this. That means the response will settle down or response will be stable after a certain value. And next is critically damped case. In critically damped case, that means zeta is equal to 1. If we put zeta is equal to 1 for this particular equation, then this imaginary part will be 0. There will be only minus zeta omega n. Now if zeta is equal to 1, so only minus omega n will be there. So only one pole in negative real axis will be there. And for critically damped case, the time response will be like this, and that means it will saturate after a certain time. So that is our time response for critically damped case. And now if we put zeta greater than 1, that means overdamped case. For this equation, if we put zeta greater than 1, suppose 1.3 or 1.5, if you put for this particular equation, then the poles will be there will be two poles which are present in the negative real axis. And for overdamped case, the time response will be like this. That means it will saturate after a certain time. So that is our time response for overdamped case. So moving to our next topic, that is pole locus of a standard second order system with variable damping ratio. Now to understand this, just look at this PP slide. Look at this slide. Here zeta is equal to 0 and the two poles are present in the imaginary axis. So here zeta is equal to 0 and the poles, that means there is a pole and there is a pole for zeta is equal to 0. So here zeta is equal to 0, there is a pole and there is a pole, complex conjugate poles in imaginary axis. Now if we increase the value of zeta, that means zeta greater than 0 but less than 1. That means the value of zeta will be in between 0 and 1. Then that means under damped case, then the poles will be here, complex conjugate with negative real axis. So here is a pole and here is a pole. So these two poles are for zeta in between 0 and 1. Zeta in between 0 and 1, here and here. Two poles are there. And if zeta is equal to 1, there is only one pole in negative real axis, that is here. Only one pole, that is here, in negative real axis. Now if we put zeta greater than 1, that means overdamped case, then the value of zeta will be negative real axis. So here is a pole and here is a pole. So we can conclude that if we increase the value of zeta from 0 to higher value, then the location of poles will shift from imaginary axis to the real axis. This is one and this is another. From, just see the red color, from imaginary axis to real axis, and then it goes towards the negative of the infinity, negative real part towards infinity, like this, if we increase the value of zeta from 0 to higher value. And this, so it forms a circle. So it can be seen that as zeta increases, the pole sketches a circular locus of radius omega n, and this circular radius, what we get, the radius of the circle is omega n. Okay, so radius omega n, and move away from imaginary axis to real axis. The locus meets the negative real axis here. Locus meets the negative real axis at omega n. That means this value, the radius of this circle is omega n. So the locus meets the negative real axis at omega n. Okay, at this point it separates but travels along the real axis. That means first it moves towards from imaginary axis to real axis, one from this end to here and one from this end to here. Okay, and if after they meet at this particular point at s is equal to minus omega n, one end moves towards negative real axis and goes towards infinity, and one end moves toward positive real axis, that means origin here. So this is our pole locus of a second order system with variable zeta, that means variable damping ratio. Now, before going to stability point or before going to stability, let us take the stability condition using rolling ball. Let us understand this first. Now, first let us take this particular figure. The base of this hollow, if this red mark represent a hollow, the base of the hollow is an equilibrium point. If the ball is displaced a small distance, and if you release from that distance the ball, it will oscillate. It will oscillate like this. It will oscillate, and after oscillation it will return to its rest position at the base as it loses its energy as a result of friction. This is therefore our stable equilibrium point. If we take this particular figure, then this is our stable equilibrium point. Okay, now if we consider this figure, now the ball is in equilibrium if placed exactly at the top of the surface. But if you displaced certain amount or certain distance in either side, the net gravitational force acting on it will cause it to roll down from the surface, and it will never return to its original position, that is top of the surface. Okay, that's why it is our unstable equilibrium position. That means, suppose at first the ball is here. Now if we move at certain amount, either this side or this side, okay, then it will move or it will roll down from the top of the surface, and it will never goes back to the top. So that is our unstable equilibrium point. And the last figure, the ball neither moves away nor returns to its equilibrium position. The flat portion represents thus the neutrally stable region. Okay, so these are all our three cases. This is our stable equilibrium state. That means it will oscillate, and after oscillation it will stable at a particular point. And this is our unstable equilibrium point, and this is our neutrally stable condition. Now, impulse response of a system. Suppose this is our forward path transfer function GS, where RS is the reference input and CS is the controlled output. So we can write the transfer function as CS by RS is equal to GS, or we can write like this, that is CS is equal to RS into GS after multiplying. So this is our equation number 1. Now if we want to calculate the impulse response of a system, or in this impulse response of this system, then we have to put the input, that is RS, as a impulse. So we already know that unit impulse is in time domain. In time domain, unit impulse is represented by RT is equal to delta t. Okay, at t is equal to 0. Now if we apply Laplace transform here, then we can find Rs is equal to 1. If Rt is equal to delta t, then by applying Laplace transform we can get Rs is equal to 1. Now if we put Rs is equal to 1 in equation number 1, then Cs is equal to Gs. We can get Cs is equal to Gs. And if we want to calculate the time response of this equation, then we have to apply inverse Laplace transform. So after applying inverse Laplace transform in this equation, we can get Ct is equal to Gt. So this is our impulse response in time domain. So Gt is called impulse response of a system. Now the transfer function of a system is the Laplace transform of its impulse response. We can say as Ct is equal to Gt. That's why you can say that transfer function of a system is the Laplace transform of the impulse response. So a system is said to be stable if the impulse response approaches to 0 for a sufficiently large time. We will see or we will understand better in our next slides. And if the impulse response approaches to infinity for a sufficiently large time, then the system is called unstable. And if the impulse response approaches to a constant value for a sufficiently large time, the system is said to be marginally stable. Now what is stable, unstable and marginally stable? To understand this better, just look at this type of figures. Here, this is our stability by pole allocation problem. Now we just take the pole, we just vary the pole positions. At first, that is our first condition, when poles are on the negative real axis. That is our pole's location. This is our imaginary axis and this is our real axis. As we all know that S is equal to sigma plus j omega. So this is our S plane and sigma is our real axis and j omega is our imaginary axis. So poles on negative real axis, that means location of poles is here. Then for this location of poles, the impulse response will be like this. That means the impulse response approaches to 0 after a certain time or a sufficiently long time. If the impulse response approaches to 0, then it is called stable. That's why this type of impulse response is called stable. That means we can say if the poles are present in the negative real axis, then the system will be stable. Okay. Now, if we shift the pole on the positive real axis, if we shift the poles in the positive real axis, then we can see that this is our new pole location. And for this particular location, if we calculate the impulse response, then it will be like this. That means it goes to infinity with increasing t. That means the value of the gt will tends to infinity for sufficiently large time. Now this condition is called as unstable condition, as this is not approaches to 0. The value will increasing with increasing t. That's why it is called unstable. So we can conclude that if the poles are present in the positive real axis, then the system will be unstable. Now, if the poles are at origin, then what will happen? If single poles are present in the origin, then the impulse response will be step response. And if there are double pole in the origin, then the impulse response will be like this, that is like a ramp signal. So in these two impulse response, both are not approaches to zero. That's why these two responses are called unstable. So we can say if the poles are present at the origin, then the system will be unstable in nature. Now, moving to our fourth point, that is if we shift the poles if the poles are present at the complex zone, if the poles are present at the complex zone with negative real axis, that means the poles are present at this region, then if we calculate the impulse response, then it will approaches to zero after increasing t. That's why it is called stable. So we can say, or we can conclude, that if the complex poles are present on the negative real axis, then the system will be stable. And if the complex poles are present in the positive real axis, then the magnitude of the impulse response will increase. Amplitude of the impulse response will increase. That's why it is called unstable. So if the poles are present in the complex poles are present in the positive real axis, then the system is unstable. And if poles are present on the imaginary axis, then the impulse response will be in sustained oscillation. And this is our marginally stable case. Not stable, not unstable, in between stable and unstable state, that is marginally stable state. So if the complex poles are present in the imaginary axis, then the system will be marginally stable. And if the repeated poles are present in the imaginary axis, then the response will be unstable. Okay, so these 1 2 3 4 5 6 7, if we conclude these 5 cases, then we can see like this. If the poles are present, this is our imaginary axis and this is our real axis. That means if poles are present in the positive real axis, that means that the red shade zone, if the poles are present in the positive real axis, then the system will be unstable. That means these red shade zone are unstable region. And if poles are present in this green zone, that is negative real axis or negative real axis, that means in quadrant 2 and 3, then the system will be in stable region. The location of the roots of the characteristics equation on the S plane will indicate the condition of stability. That means if the poles are present in the negative real axis, that means this green zone, then the system will be stable. And if the poles are present in the positive real axis, then the system will be unstable. Okay. So thank you. So that's all for today's class. In our next class, we will discuss on Raut-Harwitz criteria. There will be some special cases like row 0 or column 0 problems, and some more workout problems will be there. So thank you so much. Thank you for watching.